Hey everyone, so today we're going to talk about resolution. And I'm sure you've heard this word before, and actually what it means in physics is very, very close to what you understand it to be. So for example, when you have a phone screen, like this, when you can see the individual pixels, so imagine that, my phone screen is really bad, and, looks something like this, and I can see the individual pixels, then I say that the resolution is not very good, right? Why? Well, because, I don't know, for example, if somebody's face is like this, but I want to represent it in this screen, what's going to happen is that I'm not going to see a smooth line, right? I'm going to see something like this. So I have to color this in, color this in, color this in, and so on. Right? I'm going to see something that kind of resembles a circle, but it's not really a circle, because my screen is not able to represent this smooth line. There aren't enough points to do so. The idea is kind of similar. Now, resolution is actually very, very closely related to diffraction. And let me tell you what I mean by this. So imagine that I have a source of light, and so this is a point. Here's my source of light. This is a very, very small point, and it's giving off some light. Now, if this light goes through an aperture that's really big, it's just going to go through, and it's going to make an image in the screen. But if my aperture is quite small, what's going to happen is that this point here is actually going to make not one point in the screen, but something like this, right? And we've learned about this. This is a diffraction pattern. And of course there's some smaller minima here and whatnot, but the basic idea is that instead of seeing one point that's perfectly located, we're going to see something like a blob, something like this. And this is a problem, because this means that every time that I try to observe a point, instead of really getting a point in my screen, just because it is going through an aperture, I'm going to get something that's really not a point, but a circle. So the idea is that one point in reality goes to a circle when I get an image of it. And why is this a problem? Well, this is a problem because imagine that I'm looking at 2 points. So here I have another point right next to this one. And this one is also going to make a circle. So imagine that it makes a circle like this. And then my problem is that I can't distinguish between the blue and the white points, because they're on top of each other. So that if these things are close enough, instead of seeing 2 points, I'm just going to see a blob. So we say then that these 2 points are not resolved. The resolution of our device is not enough to distinguish between 2 points. So the idea basically then of resolution is that we say that 2 points are resolved if, when I take an image of them, I can tell between the two. If their diffraction patterns are overlapping so much that I can't tell one from the other, then we say that the points are not resolved. If they are separated just enough for me to be able to tell that these are 2 separate points, then we say that the points are just resolved. If my 2 points are very far apart, so for example, instead of getting what I have here, I get something like this, then my 2 points are basically just like they're resolved, because it's clear that I have 2 different points here. So that's the basic idea. We have either a telescope or a camera or something like that will make an image of our point somewhere here, and this image will have a certain width because of diffraction. If this is so big that I can't distinguish between this guy and the guy next to it, we say that the points are not resolved. If this is small enough that I can distinguish between the two, then the points are resolved. The idea, of course, is that an optical device needs to have the best possible resolution, which means we need to be able to look at a certain point and have a small enough diffraction pattern that we can actually distinguish between the two, because otherwise, why on earth are we using the device? So now what we want is some kind of criterion that will allow us to decide whether 2 points are resolved or not. And this seems pretty obvious, but it gets less and less obvious as they get closer. Okay, so we can all agree that these 2 points, that this is the diffraction pattern of one point, let's just say the white point, and then this is the diffraction pattern of my blue point, we can all agree that these 2 points are resolved because they're far enough, right? So it's clear that this is one point, this is another point. So that's easy. But then as I start getting this closer and closer and closer here, things get a little bit less easy to tell. Because what about when they're here? Can we distinguish between these 2 points? Well, one could argue that we can, because this has a lot less intensity than this or this. Therefore, we could see 2 pretty distinguishable points, this one and this one. So most physicists would agree with this, and then we say that these points are still resolved. If I keep putting this point this way, I will probably get to a point like here, where it's pretty clear that they're not resolved, because these 2 things have pretty much the same intensity, so I'm just going to see a blob like this, and it's just going to look like one point, so this is obviously not resolved. So there has to be a point between here and here, where we say up until there, these points are resolved, and any closer than that, they're not resolved anymore. Now, and it's arbitrary. We just had to, find a point where we said, yeah, from here on they're resolved. And what physicists use is something called the Rayleigh criterion. And this is a criterion that was, of course, invented by Rayleigh, who was a very famous optician, a physicist that deal with optics. So his criterion actually makes quite a bit of sense. He just said, look, if the maximum of this thing, so if this maximum here is at the same point as the minimum of this thing, so this is the minimum of this thing, this is the maximum, so if these 2 things are aligned, so let me make a little line here that shows that this is kind of aligned. So if this is aligned with the minimum of this diffraction pattern, then there's enough room to tell these 2 things apart. And then these things are just resolved. And this is how we call this, just resolved. Any closer, and these are not resolved. Any further apart, and these things are resolved. So basically, if we want to know whether 2 points are resolved or not, we need to take a look, okay, is the maximum of this guy further than the first minimum of this guy? If the answer is yes, then resolved or just resolved. If they're any closer, then no, we can't tell the points apart, they're not resolved. Now, I'm sure that this sounds a little bit abstract, so let's actually do an example of how I would go about finding this out. Good. So here we have a typical IB problem that's about resolution. And for this, we will only need these 2 formulas. Actually, we will need this one. But in general, you will need either the formula for the angular width, not really the width, but it's, remember, the angle of the first minimum of the diffraction pattern. This is when the aperture is rectangular, and this is when the aperture is circular. So remember, all we need to do is multiply by 1.22. And here it's important because they're talking about a woman that's looking at the thing through her eyes, and of course her eyes are round, so we're going to have to use this formula here. Okay, so we have a woman that's walking this way, and there's 2 birds here, and we want to know whether the woman is going to be able to see the 2 birds or not. Actually, we want to know at which distance she is going to be able to start seeing these 2 birds as separate points as opposed to just one blob in the distance. Okay. Now, in order to do this, what we need to do is to draw a little diagram of what her eye is going to be able to see, then figure out how the diffraction pattern works into this thing, and then after that we will come up with an equation that we will be able to solve. Because this distance will be way, way, way bigger than her eye, we will have the angle here is very, very small. So we will be able to use the small angle approximation where the sine, the angle, and the tangent are the same. And really, if you actually put this in your calculator, you will get exactly the same number. So even if you didn't use this approximation, which you don't have to use, you will still get exactly the same result that I get. Okay, so let's try to do this thing and keep that formula in mind. So we have a woman walking this way, there's a couple of birds. And they're giving us the distance between these 2 birds, and they're also giving us the diameter of the pupil and the average wavelength of the light. And we're going to need these two things because we need them for this formula here. This is the opening of the eye, so this is what's going to cause the diffraction, and this is the wavelength of the light. So of course, depending on the wavelength of the light and the opening of our pupil, we're going to get more or less diffraction. So we're going to have to use these two numbers that they're giving us. So with this number and this number, we already can figure out at what point, at what angle, the first minimum of diffraction will happen, which is here. Good. Now let's draw a little diagram to figure this out. Okay, now I'm just going to get rid of this diagram. So, of this diagram of the problem, so that I can show you the diagram, then we will go back to it. Now, here's what's happening. We have this line here. That's just the line of sight. We have one bird here, we have another bird here. This is, remember, 0.40 meters. Yeah. And then we want to see, well, here's the woman, and I'm going to, so here's going to be the woman, but instead of drawing the woman, I'm going to draw her eye as a lens, and then her retina as a screen, which is pretty much, our retina is a screen, and our eye lens is a lens. So, okay, so here, and we've done this in the IGCSE, but we will not have to use any of the lenses things from the IGCSE. All we need to know is, okay, so there's this ray of light that will go through the lens and then end up here in our retina. So I can just make a straight line going from here to here and to here. And there will be another straight line going from the other bird, again through our lens and then to our retina. And these two things will have a certain angular separation. So of course we can figure out this angle here pretty easily, because this angle here is the same as this angle here. And we know this distance. What we don't know is this thing here, which is d. So again, we know that the woman at a certain distance d will start to see these two birds as separate. We don't know what this one is. But we know that this angle theta will be the same as this angle theta. And remember that the angle is the same as the tangent because the angle is very small. So this angle is going to be just this height, which is half of 0.40. This is 0.40, so this has to be 0.20. So 0.20 meters divided by d. So this is this angle. Great. Now we also know the angle of the diffraction pattern, like the angle at which the first minimum of the diffraction pattern is going to be located. So imagine that this guy has a diffraction pattern that does something like this. So let's just draw it. Here's this guy's diffraction pattern. The maximum is of course located right where the point is. So that's not a problem. And then we want to know where the minimum has to be located. Now all we need to do to find out the position of the minimum is use this formula, where theta is 1.22, because remember, circular aperture times lambda, which we have, divided by b, which we have. They've given us both things. This is the wavelength of the light, this is the size of our opening, which is just the size of our pupil. So we can calculate this thing here. And then the next thing that we can say is like, okay, well, when are these 2 points going to be resolved? Well, when this minimum here is at the position of the maximum of this guy here. So this guy will also have a diffraction pattern, and the maximum will be centered again in the point itself. So when are these two things going to be resolved? Well, when this angular separation here, this one, so from here to the minimum of this guy, is exactly equal to this angular separation here, which is the distance, the angular distance between this guy and this guy, which is, in this case, 2 theta, because this is theta, but we want the separation between here and here. So this whole thing will be 2 theta, has to be equal to this angle here that goes from here to the minimum, so this much. So let's do this. 2 times this thing has to be equal to this thing. So 2 times 0.20 divided by d, and remember this is the tangent, but we're using it as an angle, has to be equal to 1.22 lambda over b. And we have everything. We have this, we have this. They told us that that was 550 nanometers. And we also have the opening of the eye, which is 2.5 millimeters. So really all we need to do is isolate D, and then we will know at which distance these 2 points are separated. I can do this in a second. If we just plug in the values into a calculator, first thing I'm going to isolate D. So D is going to go over here. So I will have 2 times 0.20 equals 1.22 lambda over B times D. And then I'm going to put all this stuff under here. And remember that if B is dividing, it's going to go there multiplying. So I'm going to have D equals B times 2 times 0.20. And I'm doing this very slowly so that nobody gets lost. And then divided by 1.22 times lambda. And all we need to do now is plug in the numbers. And if you do this, you will get that D is more or less equal to 1,500 meters. Which means that the woman is going to start seeing those 2 birds as separate at this distance here. So I hope you got the idea. What matters is comparing the angle of separation between 2 points to the angle of the first minimum of the diffraction pattern. And then if they're equal, then they're just resolved. If one is bigger than the other, then the points are resolved. If this angle is smaller than from here to here, then what we have is points that are not resolved anymore. Now, we also need to talk about the resolution of a diffraction grating. And if you remember, a diffraction grating is just a bunch of slits, lots and lots and lots of them, very, very thin, that cause a pattern that's very, very similar to that of a double slit interference pattern, but the slits are very, very thin. So we have one wavelength will do something like this, and the separation is always the same, and it depends on the wavelength. Now, the cool thing about diffraction gratings, as I told you, is that I can use them to separate wavelengths. So if I have another wavelength here, then what's going to happen is that I'm going to get these guys separated, because the separation between each one of these things depends on the wavelength. And of course, each one of these guys are going to be at a different distance, because one is order 1, then 2, 3, 4, so each maximum is at a different order. Let's call that order M. Yes, or 1, 2, 3, 4, 5, whatever. So what I want this thing to do is to be able to separate wavelengths that are very, very close together, because that's why I bought my diffraction grating. I bought it so that I could get some light shining through it and separate it into its constituent wavelengths. So I wanted to be able to tell me when there are 2 different wavelengths, even if they're very, very close together. So in order to figure out how powerful a diffraction grating is, we need some kind of number that will tell us that. And we call that the resolving power of a diffraction grating, and we call it R. So, but see, this is different from when we had 2 points and we wanted to know whether they're resolved. In this case, we're not talking about whether 2 points are next to each other. We're really talking about, can this thing tell between 2 wavelengths that are very close together? So, of course, the smaller the difference this guy can detect, the more resolving power it's going to have, right? So this has to be equal to something divided by the smallest difference it can detect. And ideally, this should be a number without dimensions. So if we are comparing the smallest difference in wavelength that it can detect with something, here there should be some wavelength. Now, we could take any wavelength, but in order to be fair, we're going to take the average wavelength that goes through here, so that we're really taking a look at the comparison between the smallest difference in wavelength that it can detect compared to how big the wavelength is that's coming through there. So here I'm going to put the average wavelength that's going through the diffraction grating. And this is just the definition of the resolving power of a diffraction grating, and we just need to know it. Now, it turns out that you can prove that this resolving power depends on 2 things. First thing, it depends on the number of slits. And of course it does, because remember that the more slits we have, the thinner these minima become. So if these guys are, these maxima become. And if these guys are very, very thin, then of course you'll be able to tell between this guy and the next. If these guys are very, very coarse, then you won't be able to tell between this guy and the next. this also depends on the order. Remember that the order is how far we are from, let's say, the center. And of course, the further you are from the center, well, the distance between these two lines starts to change. So we need to take this into account too. Now, it can be proved, and I will not bother proving this because it would take a really long while and it would really not make a lot of difference to your understanding, that the resolving power of a diffraction grating is equal to the order that I'm trying to observe, so either first order, second order, third order, and whatnot, times the number of slits that we have. Now, what I can do is I can combine this thing with this thing here, so that I can get average wavelength divided by smallest wavelength difference that I can detect equals m times n. And then I can rearrange this to figure out the smallest difference in wavelength that I can detect, so that I can get that the difference in wavelength is the average wavelength divided by mn. And that's pretty much all we need to know about the resolution of a diffraction grating. Again, it's about separating two very close wavelengths. So that's pretty much it. After having watched this video, this is what you should be able to do. First thing, you should be able to explain what we mean when we say that two things are resolved. What do we mean by resolution? And then you should be able to state and apply the Rayleigh criterion. So what do we mean by the Rayleigh criterion? And then apply it in different situations, like the one with the woman and the two birds. And finally, you need to be able to find the resolution of a diffraction grating, or conversely, sometimes they will tell you what is the smallest difference in wavelength that this can detect. And then if you know the average and you know the resolving power, then you will be able to figure that out. As I said, this is a short topic that seems to confuse the students. I hope with this video I made things a little less confusing than last year. If not, we can talk about it in class and I'll help you out. I'll see you soon.